Welcome to the lecture on color within the course on computer graphics at KAUST. After we have made ourselves familiar with what the light is, now the second step will be to understand how this light is being sensed on the side of the observer. When we perceive a daily radiation of the visible light, the entire spectrum, we typically do not see photons associated with one wavelength, but photons associated with all wavelengths within the visible spectrum, and of course beyond it as well. But those we cannot perceive due to our visual system limitations. Now, what we can create is a kind of a histogram that will tell us how much of a particular wavelength is represented in a given light. And this light can be a direct illuminant. This light can be a reflected light from a surface of a particular material, of a particular object. This is characterizing as the reflection of or the particular emission of a particular light source or a material. Now, we are not able with our visual system to perceive all these wavelengths independently because our visual system doesn't feature enough of sensors that would be capable of discriminating all these different wavelengths. And there is a certain projection from the space of all visible wavelengths and their corresponding intensities into a limited dimensional space of represented by our sensors. And this, we have three photoreceptors for the daily light, which are able to sense a certain stimulus, and which is then reflected by the level of excitations of certain neurons. We can map this stimulus of three independent types of photoreceptors onto three different channels. Therefore, as a consequence, we came up with models such as the RGB representation of a color. But more on that later. If we would like to perform a more physically realistic rendering with all various effects which are possibly happening with light, then we will need to expand the amount of channels for which we are considering during the rendering pipeline into much more than just three. And we would need to develop something like a spectral renderer. These types of renderers are being implemented for very specific applications when particular special effects of light are taken into account, such as interference, etc. I have told you that the human visual system features three different photorecepting sensors. And that is true. There are three different cones which are responsible for daylight. Except of that, we have also another type of photoreceptor which are called the rods, which perform are active in the night vision and are colorless. So they are not different types, and they are of just one type. Therefore, they can only sort of encode the intensity, which they do, but only if it's very dark, like, for example, a scene which is illuminated only by a moon, for example. The cones, on the other hand, are active during the daylight and the normal conditions which we experience, and during the time the rods are practically inactive. There are three types of cones, and each of these three types have a certain sensibility distribution over the visible light spectrum. One type is called the short wavelength cone type, which is sensitive mostly to the short wavelengths, which are various hues of blue down to the ultraviolet. Then we have medium wavelength cone type, which is mostly sensitive to the wavelengths which we perceive as green. And then there are long wavelength. There is a long wavelength cone type, which is sensitive to wavelengths which are close to the infrared spectrum, and we perceive these sensations of such wavelengths as the red color. And while this is very typical for the standard human, there might be some exceptions. For example, it is known that 5% of the male population is missing one of these cone types and therefore has a limited color vision. These individuals can still perceive some variations of color, but not the same as the majority of the population. And we refer to that as a visual deficiency, colloquially as color blindness. On the other hand, it is speculated that some parts of the female population have one more cone type, which is even more specific than the three ones. So it's really a fourth, and therefore these women would have more, even stronger color sensation. It is known that, for example, birds have one more cone type, have 4 types of cones, and therefore they can discriminate even more colors. And what is this useful for? Well, the discrimination of a color as a reflection of wavelengths from a particular material, it was evolutionarily important to discriminate objects which are otherwise of the same shape. Imagine some berries which are the same in appearance besides their color, if you like, or the spectrum that they reflect and absorb. And in order to be able to discriminate a poisonous berry from a good one, for that it will be necessary to have this capability. So this has been an evolutionary advantage, and therefore the sensation of color has evolved. We can say that the color vividness is maybe mostly developed from birds, but then the primates have 3 different cones, and other animals would have a smaller space on which the visible light spectrum is being projected, and therefore have less vivid color vision. So it is important to understand that color as such is not really existent in the nature. It is a projection of the photons which are reaching the eye, the retina, at various intensities. And these various intensities over the visible light spectrum are simply then projected onto a space where only 3 values are then more conveying or encoding this entire visible light spectrum, which was much more dimensional. And therefore, we can see how can we calculate this transition between the visible spectrum intensities and the sensation of the color. It can be shown here. While the this graph on the right-hand side is showing three different cone types: the short wavelengths cone type, the mid wavelengths cone type, and the long wavelengths cone type. These all three different cone types are having different sensitivity and absolute sensitivity. So what we can see here, it is scaling to a relative sensitivity from 0 to 1. So their mutual sensitivity will be different. We are, for example, less sensitive to blue and the various intensities of the short wavelengths as opposed to the green and mid wavelength intensities. But on the percentual level, here we can calculate how are we sensitive to a particular wavelength. So imagine that we have a visible light spectrum, something like this here, and then our response, our perceptual response from the photoreceptors will be basically the integral of this visible light spectrum with the multiplied by the weights from our different cone receptors, how sensitive they are to a particular wavelength. So you can see that this part will be will be multiplied with the values which are corresponding to the short wavelengths. They will be weighted quite highly, while this part of the visible light spectrum for this cone type will not contribute much, so it will not excite it very much. If we will have, for example, such a sensation, this cone type, the short wavelength cone type, will have a very low sensation. So the more of the wavelengths are in the short wavelength spectrum, the more excited this cone type will be. The same holds, I will delete it now so that we can see it for the other cones. The same holds for these other cone types. So the highest sensitivity is given by the mid wavelength, and you can see that it is practically, this mid wavelength is even sensitive to very long wavelengths, but sensitive just a very little bit. It is mostly sensitive to the wavelength 555. There it's where this sensation will be the highest. And the long wavelength cone type, which has been evolutionary developed from the mid wavelength cone type, is just slightly shifted towards the long wavelength and is having stronger signal for the sort of colors which are associated with red, or with the wavelengths which are associated with red color. We can see this graphical representation described here formally through the integrals, where our description of visible light spectrum encoded by this function phi and is for each wavelength multiplied with the cone type excitation factor for that particular wavelength. And we are summing up all these wavelength excitations to have an overall number of excitations for the, in this case, long wavelength cone type. And the same holds for the mid wavelength cone types and the short wavelength cone types. So So at the end of the day, based on a certain stimulus, which is represented as a spectrum of colors, we have then three numbers, you could say, of excitation levels for the long, mid, and short wavelength cone types. So we have three numbers, a three-dimensional vector, which can then be represented or used for representing our encoding of color. This aggregated response from these three cones leads to the so-called three-stimulus theory, which defines that we can generate a color stimulus of an given spectrum of wavelengths just by matching them by a mixture of three colors, of three modulated color sources. And if we have such a stimulus, then the following holds. If we have a stimulus of different wavelength intensity profiles for each wavelength, but the color stimulus is considered as matching, meaning that we perceive this different wavelength distribution as the same color, then if we find that A is matching B, then obviously the B is matching A. And if we, there also the transitive rule applies. If A stimulus is matching the B stimulus and the B stimulus is matching the C stimulus, then the A stimulus is matching the C stimulus. So the transitive rule applies. The proportionality says that if we see a match of a stimulus and another A with B, their scaled versions should also be in a match. And the additivity property tells us that if we have a match of stimulus A and B and C and D, then the additive addition of the two colors stimuli A and C and B and D will be also matching to A and D and B and C. So we can see that even if we will have different input, we oftentimes might have the same sensation through our perceptual mechanisms. And this is defined in the so-called Grassmann's laws of trichromatic generalization. And when we were talking about different stimuli, we can see this clearly on this example here. We have here two stimuli, two profiles of wavelength distributions in some light or some reflected light. And we can see that the sum, the multiplication of the phi 1 with the cone S will lead to the same number as an integral of the various wavelengths as with the phi 2. And the same will hold for the long and mid wavelength cones. So the response for the L, M, and S for these two different input signals will be the same. Consequently, this means that these two colors will be considered as identical from our perceptual perspective. If we will have higher precision in our visual system and have one more cone type, we will then notice the difference. But with our hardware, if you like, we will consider them as identical. And therefore, there has been experiments in color research with replacing the colors with three lights, which are called the primary color, which are then added together in forming a different color. And they are added with different intensities. So we can manipulate, we have three lights. Let's say, imagine you have a projection of a red light and a projection of a green light and a blue light, and you mix them together, and then you can modulate each channel, each intensity of each of these three lights, and by that you can vary uh, the, the, the resulting mixed color, and you would like to see whether we can, with this approach, generate a sensation which will be identical to a fourth color, which will be just a color that is uh, pure uh, color that is not a mix of colors, but it is a one of the spectral wavelengths, whether we can generate the sensation with the mix of three colors, which will be identical to the sensation of the fourth color, which is just a pure color of one single wavelength, or with a short, very short interval of wavelengths. So these experiments were then conducted in order to find out whether we are capable of representing all possible wavelengths, all possible visible light intervals with just three primary colors. And this capability obviously depends on how we choose these three primaries. If all of them will be in the, let's say, the short wavelength spectrum, we will not be really able to generate green or red sensation. So it naturally, we will need to have a well-distributed representations of these three primaries over the visible light spectrum. And so the scientists back in earlier 20th century have decided to conduct such experiments. They have chosen three primaries, one of a short wavelength representative, one mid wavelength, which is associated with very high sensation, and one with the long wavelengths, which is somewhat at the border of the visible light spectrum. So with this well-balanced distribution of wavelengths, they were trying to reproduce the sensation of other wavelengths in between. And what they have done practically was that they had a kind of a half circle, if you like, and on this half circle they had three projectors of these primary colors. Sorry. So this would be the, let's say, the R, G, and B, where the R will be the 700 and the G will be 546 and the B will be of wavelength 435. And then we have the second half circle, and the second half circle is just projected with a single wavelength. And the question was whether we can reproduce such a difference of intensities of the R, G, and B so that there will be an indistinguishable border, or these colors will be indistinguishable from themselves. If so, then we can fully reproduce the sensation of that particular wavelength. And they have started with this experimentation, and they realized that this is indeed possible for several colors. However, there is a problem with one of these colors, and namely the R primary, the long wavelength. If we wanted to reproduce certain colors in the between the around the green-blue interface, these R wavelengths needed to be negative. Well, this is of course nonsense. We cannot have a negative light energy. This was represented in a slightly or reformulated in a slightly different way, which I will show you in a moment. But the answer is, in general, with these three primaries, we were not able to represent the entire visible spectrum. This was not possible. Only of wavelengths, certain subset was successful, but there was a certain region where this was not successful, and some additional modifications are needed in order to create a practical tree stimulus theory, so that we do not need to deal with negative energy. So what was done here in this experiment? In this experiment, as I drew it on the previous slide, you can see that we have the three primaries, and we are trying to represent one spectral color of a single wavelength or a very narrow band of wavelengths. We are trying to reproduce the identical stimulus through our three primaries. And we see that sometimes it's not possible, and we have to, in fact, not instead of having the negative contribution of the red long wavelength sensation, we have to add that color on this side. So if we add that color, we can then see that we have basically, if we add the color on the other side of the equation quasi, then we would practically subtract it on the other side of the equation. So that would be identical. We can see it here, where you can see that now there is a certain contribution, certain intensity of the green and a certain intensity of the blue, and no zero intensity of the red color, so to say. But our wavelength is our pure color is now even more vivid than the green color which we started out with. So how can we represent even more vivid green than green which we have? That doesn't work, and therefore we have to limit its sort of vividness into more of an olive shade by adding the contributions from the red side on the other side. So the answer is that with the tree stimulus theory, we cannot really represent the all possible wavelengths of light, but a reasonable range of it. And we need to do something else in order to be able to represent all colors, all visible light spectrum sensations. So you can see how the various intensities are varying in this animation here, and you can see in the steps of this animation how does it sort of correspond to the intensities on this graph. And you can see that when we are here on the negative side, then we have the red light on the other side of the mixing up with our pure varying wavelength, which we are trying to match. All right. So this leads to the fact that if we plot now these red, green, and blue functions in 3 dimensions and create sort of concatenated into a point, we will end up with a representation here, which I will draw somehow quickly, where we have, or like this, where this is a 0, 0 point, and we see that for the y-axis we are always positive, but for the x-axis, which is the r, we are sometimes negative, as it is described also here. And for the blue, for the z-axis, so the z, we are also always positive. So this leads to a certain impracticability of having a negative color. And what we can imagine to do with this problem is to reformulate the geometry so that we will not have to deal with a negative color coordinate, but we'll have always positive coordinates if we would like to express a certain color. And how can we deal with that? Well, we can simply express our colors within a different coordinate system, within a mix of different primaries. And these primaries can actually be virtual primaries. So the primaries will be something which doesn't exist physically. They are virtual, and such light doesn't exist. We cannot perceive such light, but we can basically create the triangle spanned by these virtual primaries, into which all our colors, which we can perceive from the previous experiment, will fit. So this means that we will have the good values, all positive values for all the colors we can sense. The negative thing is that we unfortunately cannot use these primaries because no device can generate it so that we will be able to perceive these colors. So this is physically not realizable, but it is mathematically practical so that we can always convert into this color system with virtual primaries if we are converting between other systems of colors. So once we have the virtual or imaginary primaries, then we can reproduce any color without having the notion of the negative light. And with this, we will be associating new functions which will be defining the amount of sensation of particular matching function. These matching functions are no longer associated directly with the cones, but are somehow remotely similar to those. So it is a remapping from a one coordinate system defined by one triangle to another coordinate system defined by another triangle. And in these color matching functions, we define as such that the y color matching function is actually equals to the photoscopic luminance response function, V lambda. This means this is the achromatic component. So we would like to have a separation into chromatic components of the color and an achromatic component which encodes the luminance. And all these experiments have been done on humans and who have a normal color vision, and they have been averaged to respond to correspond to something which is called the standard observer, which is the average behavior of a human. We need to keep in mind that every individual has its individual visual perception characteristics, and they are not identical. They are even changing within the lifetime of one individual. So if we have our RGB coordinates within our caused by our primaries, meaning the intensities of these individual components, so that we are mixing up to a particular color, these can be reformulated through this matrix multiplication and scaling into the XYZ coordinates of our imaginary primaries. And through that, the reformulation using our imaginary primaries will also change how our functions are being defined where we see that the long wavelength function is no longer negative. It has a minimum value in the region where it was negative before, but it is not negative anymore. And similar, the function for short wavelengths has changed, has been scaled up, and the function for the mid wavelengths is identical with the luminance sensitivity function. So this is the recalculation into the XYZ coordinates of our imaginary primary color space, which we term into the CIEXYZ color space. The CIEXYZ color space is a three-dimensional color space. And if we will be varying the individual values in X, Y, and Z, then we will be changing the values in the three-dimensional components of various colors, where all the colors will be represented, and also some combinations of X, Y, Z will not be corresponding to any color because they will be outside the possible color range. This color space we would like to decompose into its chromatic component and the luminance component of it. And we can do so by simply projecting the X, Y, and Z components onto the so-called chromatic plane, where we will be dividing the values of individual color components by the sum of their components. And then through this sort of normalization, we will have the X and Y components, and then the Z component, in fact, will be no longer necessary for defining this two-dimensional chromatic plane, because it will be redundant, and we can see that the sum of X and Y can determine the Z, because XY plus Y plus Z is equal to 1. So therefore, we are dropping the Z component, and instead, in this color space, we will be defining, where we have here this X and Y, the third dimension will be the Y, the luminance sensitivity function, which will form the entire color space. In this color space, you can see that all the pure spectral colors of particular wavelengths can be defined by a certain X and Y values, such as in this case we can see that the value of 400 nanometers wavelength can be defined by some coordinates between X and Y. Keep in mind that these X and Y are now coming from these imaginary primaries, and there are certain regions of X and Y which are not determining as any color. So the border of colors is defined by this border where all the colors are somehow represented, which are the pure spectral colors originating from a single wavelength. So we can see that here in the bottom are the short wavelength colors. Now in this region we would have the mid wavelength colors, and towards the end of this curve we will have the long wavelength colors corresponding to the red. We can also see the connection between the 700 nanometers and the 400 nanometers. Here is a gradient of violet colors. Interestingly, these colors are not a pure spectral colors. These are mixtures between the blue and the red colors, or the short wavelength stimuli and the long wavelength stimuli, by a combination of these. And in fact, in this color space, you can perform any connection, any combination of the spectral colors, and by varying their intensities, you can vary change of the colors along the line of between two different pure wavelength colors. So, for example, you can also define here three primaries. You could have your own primaries, which will then define our smaller part of our color space. The primaries could be typically some pure wavelength colors, but could also be a mixture of colors, which is then defining a subset of the color space. So we see that we have now defined the CYY color space, and we can compute the individual components as described by the projection, and we can also get back to our x, y, z coordinates, provided that we have the y component available from the previous color space. So the y is remaining, while the x and y are the chromaticity plane. Now, so the x component can be computed as a fraction between x and y multiplied by the y, and z can be obtained by the 1 minus x minus y, which is the small z, divided by y, and times the y component of the luminance. So, and within our color space, we can here define the so-called gamuts, the individual areas of individual devices which will be capable to be reproduced by certain hardware. So, for example, we can have here the gamut of the CIE RGB, which will be somewhere here, and 540 and 700. So you can see that the CIE RGB is covering a lot of the colors, but not all of them. There are some which cannot be completely reproduced. Then we have some smaller gamuts, like for example the HDTV will have a smaller gamut of reproducible colors, and all the colors in between can be then created by the mixture of these individual colors and their intensities. So we can obtain here any colors through the so-called additive color mixing. Here are the approximate drawings of the large gamut CIE RGB, so I was not exact, and the small gamut of the HDTV, which is depicted here. So we can see that this chromaticity diagram has, besides its chromaticity, this chromaticity is changing based on how close it is to the border. So the closer we are to the border, the more pure colors we have, and in between we have a mix of colors. For example, we can achieve mix of colors which will be passing through the point E, which is our white point. I mean, it doesn't need to be white for a particular level of chroma. It could be gray, but it will be not a saturated color. It will be just a luminance color. It will correspond to a shade of gray. This chromaticity diagram is already useful in many cases. It is lacking one aspect which is not optimal. The scale how this chromaticity diagram is depicted is not reflecting the fact of different sensitivities to various wavelengths. So it means that if we will be within our chromaticity diagram somewhere at some position, and we will be moving in any direction, there will be different sensations of a change of a color. This has been studied in the psychophysics studies by the notion of the just noticeable difference. So imagine that you are looking at a particular color, and then you will be just observing its very neighbors, and you will be stating whether you can see that these two colors are different. The reference one, and its intermediate neighbor, very close to it. And once there is a notion of a difference of color, even the very slightest, that is the measure of the just noticeable difference. In this CIE XYY color space, this is not the case. So there is just noticeable difference in one direction, will be much larger vector than in other directions. And therefore, a particular scaling would be necessary to make it more perceptually linear. This means that we will be then able to go in any direction in the new perceptually linear color space, and the step will be associated with the same level of contrast, the same level of change in color. Of course, not the same color will be seen at a different part of this color space, but it will be the same change of color sensation. And for that, we can use the so-called LUV color space, where the L will be equal to the Y, to the capital Y, and the U and V is defined through these following equations. So they are similar to those which we had before for the XYZ to XYY color space conversion, but the UV has a slightly different scaling factors, as we can see here, for the U and for V. And these scaling factors reflect our sensitivity to various types of wavelengths. And we can see that the scaling of our CIEL XYY color space into CIELUV color space is now changing, and it has been shrunk. Especially the green region has been shrunk significantly. I'll just delete this because it doesn't correspond to this diagram anymore. All right, so we can see by defining before the color space with the XYZ primaries, virtual or imaginary primaries, or the CIE RGB primaries, or the HDTV color space, or the LUV color space, that we have several color spaces, and we often need to deal with those. For example, for the printers, we would also have a color space, but for subtractive definition of colors. So a subtractive color space will have the primaries CMYK, meaning that there will be an cyan, magenta, Y, and black. So there are 4 different primaries, and they are forming a more complex 3-dimensional gamut in our color space. But now, how can we relate the coordinates of CMYK values to, let's say, LUV? And for that, it turns out that the practical utilization of this abstract XYZ color space could be used for that. So it is considered as a device-independent color space for conversion between color spaces. So if you have something defined in RGB color space and you want to know the corresponding CMYK colors, you first, because your colors might not be fully reflecting it in one or the other gamut, gamuts. One gamut might be larger than the other one in certain regions, but definitely not for the XYZ color space, because there this is a color space which is larger with its gamut than any other color space. So we convert it to the XYZ, and then we can convert it to another color space, like for example the CMYK, so that we can instruct the printer to print a picture. There are different reasons for different color spaces. I already mentioned the CMYK for printing because we are dealing with subtractive color space. The subtractive means that we are starting with white, such as white paper, and by adding pigment, we are limiting the spectrum of light which is reflected from this paper. So we will be, by adding some red pigment, we will be blocking all the other colors, only the long wavelength associated signal will be reflected from the paper. So that it means that we are subtracting from the visible light spectrum only some subpart by this by printing with these pigments. Then there are other reasons. For example, we would like to have efficient encoding. We like to have the RGB color space for various computational reasons. For perceptual uniformity, we will probably like to use the LUV color space. And for intuitive color specification, there could be yet other color spaces. As we were discussing the CMYK color space, we can see how it is realized on a white background. So to say, we are subtracting what is reflected from such a diffuse material. So if we have a yellow filter, then we will see on everything which corresponds to the short, long wavelengths and the mid wavelengths. So the yellow color will be the only one which will be reaching our eye, which means it's a spectrum between mid and long wavelengths. If we even more limit it, then we can see here only the very long wavelengths, and the magenta color is a color which is associated with the mix of colors between the blue and red. So magenta is a combination of blue and red, and if we subtract the magenta pigment from the white diffuse paper and, for example, the cyan, then we will obtain a blue color. So this way we can print our pigments on the paper. However, we need to keep in mind that this is a subtractive color model, although we are adding pigment, but this adding pigment reduces the capability of reflecting the entire spectrum of a white paper towards us. We can see here that there are several color spaces defined. We can see that the CMYK color space is, for example, here, which results on the chromaticity diagram into this very complex gamut, because it's not three-dimensional, but not only CMY, but also it has the K for the black pigment. Then there are some other, like the sRGB, and you see that this is not defined as a pure spectral color, which will be corresponding to one wavelength only, but it is a mix of wavelengths, which is then defining one of its primaries. Interestingly, there is Adobe has a wider gamut, and there is even a larger gamut in this Profoto standard, which defines actually two primaries outside the space of possible colors or possible visible light wavelengths. Then there are some other spaces like the HSV color space, which is defining the hue in a circle like we see here, and then the saturation of colors is in one dimension, and the value, which is the intensity, is in the third dimension. And this is very practical color space for content creators. It's somehow here we see the luminance direction, and we can somehow see how this representation fits or can be scaled towards the chromaticity diagram. But this color space has the advantage that for artists, they can define along the, for example, the value axis, what is the corresponding shaded version of a particular color. So if I have a white material in my painting, and then part of this material is in shadow, then I can pick by just reducing the value, I can pick a color which should correspond to the shadow. And that's for the achromatic component. But this also works for other components, so that we have other colors. Like for example, for this blue one, we can also see that we have some highlight color of the blue, then we have the major tone of the blue, and then the same blue color is in the shadow. So in this, we can easily identify colors within this color space, which are then consistent with the painter's theory of color mixing. If we would like to create a transform for a particular device and its gamut from its color space to the XYZ color space, then what we will do, we will take the, let's say, RGB coordinates, and for each R, G, and B, we will calculate their corresponding coordinates in our chromaticity diagram. So if we have the triplet RGB, and we will just have maximal R and 0G and 0B, in this case, for example, we will be computing the coordinates on this chromaticity diagram, which looked, for example, for the XYY approximately like this. We will find the coordinates for X and Y. And then we will have, maybe it will be somewhere here, the coordinates will be particular X and particular Y, which are then stored here as this two-dimensional vector. The same we will do for the G of our device, and also for the B of our device, and we will store their chromaticity coordinates. Also, if we turn on all the three colors to their maximal degree, so R, G, and B will be 1, 1, 1, this will be defining the maximal value of our white point with also the highest intensity. And this value can also find its place on the chromaticity diagram. If we moreover know what is its highest value, then we can calculate from this the corresponding values. So if we know for the white point the maximal luminance, from that we can calculate the values for X and also the values for Z of the white point. Once we have this information and we extend our two-dimensional definition of colors back to the X, Y, Z, all small letters, where the Z equals 1 minus X minus Y, then we can form a matrix transform based on the white white point, so that we can convert any color defined by the RGB coordinates into the X, Y, Z coordinates. So once we know the X, capital Y, and capital Z coordinates of our white point, which we can have calculated on our previous slide, and at the same time, we have the coordinates of XR and YR, and we calculate to it the ZR by Y minus X and Y. And the same we know for the G coordinates, and we also know it for the B. Then we have just three unknown in this linear system, and we can create a matrix with with this SR, the scaling factors, and SG and SB will be calculated. And once we know this, then we are able to calculate the XYZ coordinates of our R point, or G point or primary, and B primary, which can be obtained by simple multiplication of this component with the small XYZ coordinates of our primaries. These factors we can then store in a conversion matrix, and this conversion matrix is then useful for expressing any coordinates of our RGB to be converted into the XYZ coordinates. So with help of the luminance value of our white point and the chromaticity coordinates of R, G, and B, we can reconstruct first the XYZ coordinates of our white point, the capital XYZ coordinates, and then, based on this white point, we can reconstruct the XYZ coordinates of the R, G, and B, and create the conversion matrix, which will be transforming our RGB space, which is a particular one for a device, into the XYZ coordinates. We can see one practical example of this using the sRGB color space, which was developed by Microsoft, where we have the R component has the chromaticity values stored here, XY, G has the chromaticity values here, and B has the chromaticity values stored here. The white points chromaticity values are stored here, and we also know that by the maximal level of the highest strength will be obtained by the 100 values in our RGB space, and the Y will be associated with 100 candela per square meter. So this is the highest luminance which we can achieve. And based on this information, using the framework which we described on the previous slide, we can calculate ourselves the conversion to the RGB, from RGB to the XYZ color space. And as we said, the conversion to the XYZ color space in itself is not useful because we cannot represent the XYZ coordinates, but we would like to use it for converting from one color space into another color space. So, for example, if we can have the sRGB color space, or the Adobe RGB color space, which has slightly different primaries, the HDTV color space, the NTSC color space, the PAL SECAM color space. all these are slightly different, and calculating between those, if you want to have one material from one color space to be presented on another color space device, then you should undergo the conversion with the XYZ through the XYZ color space. One thing which is important to keep in mind is that not all colors are then representable in the destination color space, and we need to do something about that. And that mapping can be realized, for example, through clipping, which would be probably the most simple approach to define the conversion of colors which are not representable on the target device. One more color space, which is particularly interesting, is the CIE-LAB color space. This color space is perceptually linear color space, and with respect to the standard observer, and it is based on the so-called color opponency. So the L component is the luminance, which is the achromatic component, and that corresponds to the one channel. And then the other two channels, A and B, are representing us the color opponency between red and green and yellow and blue axis. So if you imagine our representation of the XY chromaticity diagram, in this we had before the absolute coordinates, if you like, of a certain point in this two-dimensional space. But in the LAB color space, we are basically interested in the position along one axis between green and red, and another axis between blue and yellow. And 0 will be associated with the white point, and the more blue the color is, the more negative the B will be, and the more yellowish the color will be, the higher value will be associated with B. On the red-green color opponency, the more red the color is, the higher value for A, and the more green the color is, the more negative value for A. So this is a definition of the color opponency, because we know that we have some color opponency mechanism in our perceptual system. While if I tell you that imagine a color which is somehow between green and blue, you can imagine a color which is something like cyan. If I tell you imagine a color which is between yellow and red, you will be able to imagine between yellow and red is something like orange color. But if I ask you what is the color halfway between blue and yellow, if you mix blue and yellow, there is no such color in our imagination. Or what is the color if I mix green and red? What is the name of such color? We do not have an association with that, and in fact, it will be at the midpoint of these color components, there will be a gray color, or no color, you could say, because there is a 0 chromatic component. So with this color space is intuitive from understanding of where you are within the color opponency, but it also has a very favorable aspect, that it brings the appearance into the game, as we will see on the next slide. CIE-LAB is a perceptually uniform color space, and therefore it might be advantageous when considering to convert between two color spaces, such as the RGB on our monitor or of an image which is stored on a computer, and the CMYK, which directs our printer to define how much color should be or pigment should be deposited at a particular position on the paper. It will be to preserve the same vividness. The perceptually uniform color space will be of advantage to act as the common space for the conversion. You can see here the difference in vividness of colors when using the CIE-LAB, or if we are using some other ways of converting between the additive and subtractive color spaces. If we would like to convert from the XYZ color space to LAB, we cannot do it right away just from the XYZ values of a particular color. We would need to it an additional color of a white reflecting diffuse surface under a known illuminant with these colors defined in the XYZ color space. This means that we can sort of define a white point in the LAB color space, and that also defines us where is our axis of the color or opponency. So for this, the benefit of the LAB is that it is perceptually uniform, but also it can be helpful for changing the light balances, and which will be changing the color space conversion as well. We can see how it can be computed from the XYZ color space by having the X, Y, and Z coordinates first divided by our known illuminant, and then, which is illuminating the white reflecting diffuse surface and the color of it. And then we are having the argument of this function here is having a certain having two functions, is a composite function of two functions, where one function is this expression and the second function is this, based on whether R is bigger than 0.88 or smaller. And if we have a look at our matrix, we can see there that our LAB color space for the L, we will be interested in the Y component, and this Y component will be weighted with the strongest amount. And then there will be some subtraction of 16 here, but the L, the luminance, is basically taken from the Y, which is associated with the luminance in the XYZ color space. For the A, we can see that the first two components are basically defining the color opponency, and for the B, we have the second and third component defining the color opponency. And this is how the LAB values are being determined, also with this complex function here. So as you see, we have the L standing for the luminance or for the lightness. The chromatic channels A and B are the color opponent channels, which are dependent on the luminance that is defined by also the white balancing. In this perceptually uniform color space, we can perform and define certain distances. So the distance can be defined as a Euclidean distance between the components, and it will define an overall contrast between two colors. So we will have a contrast of the luminance part summed up with the color chromatic parts here, resulting in the overall distance between two colors. So we have a metric here where we can use a Euclidean distance to express the difference of colors in this perceptually uniform color space. What the LAB color space does is that it starts to take into account the environment in which a particular image is being viewed, or in which environment the image is taken and then viewed in another environment. As we typically can experience various lighting conditions, we often still can, under very drastic conditions, still can recognize the original colors or perceive the original colors. Imagine just a candlelight dinner and the colors which are available there. From the candlelight, you will have just these very warm light colors because the light is somehow yellowish, but despite that, our objects will be still having their colors as we are used to them. And if we have the same scene, but we suddenly turn on the light, which will be maybe the regular electric light, or there will be a sun coming into the scene, we will have a totally different spectrum distribution, and but we will still see the same colors which we are used to. Also, when we are submerging underwater and in a distance from at a certain depth, we will perceive still the colors which are there, despite the fact that there is just a very different illumination due to the absorption and reflection of many parts of the visible light wavelength from the surface of the water. So, and this is called the chromatic adaptation, that we are still able to represent different colors or perceive different colors actually as being the same ones, or the same material being the same under different light conditions. And this is somehow, this chromatic adaptation is somehow a biological equivalent to white balancing. Let's have a look how this can be modeled. I didn't cover that, and this is in the book. There is something called the LMS color space, which is the long, middle, and short wavelength cones color space. And we have, again, a matrix for a conversion from one color space, from LMS color space to XYZ, and the other way around. And the chromatic adaptation can be actually done in to such an extent that you see various points plotted in this drawing here. These all points, they have very different colors, but under these lights considered as white lights, we can all perceive, or the standard observer can perceive, the same color of the objects in the scene. So the chromatic adaptation is quite, makes our perception quite flexible. And this can be modeled in such a way that based on we are sort of tweaking the sensitivity of our cones based on the white balancing. So these cones will be shrinking or increasing based on how much they are sort of already sensed by the white balance example. And from that, we can infer these alpha, beta, and gamma gain scalars, which can then rescale our situation to the one under particular white balance. So we can see here that this green line will be a distribution of the wavelengths in the scene, and this will be our white light in the scene. And based on this, all these peaks will be scaled, and the more there is the part, the more the light contains this or the cone is excited by these wavelengths which are participating on this wide light spectrum, the more the sensitivity will be shrunk for that particular cone type. And we can see it modeled in this matrix where we have our white light values, and the reciprocals of them will be forming as the alpha, beta, and gamma. So that we have the resulting L and S components, which are already corrected for the white balancing. So this way we can model, have a simple model of a chromatic adaptation. If we have two scenes and we would like to have an transfer from one scene with particular white point to another scene with another white point, we can go further and first change the white point to be gaining those cones which are suppressing the sensitivity of those cones which are mostly affected by the white balance part of the spectrum, and then we perform the inverse scaling with the new white balanced spectrum of the new space in which we want to present the same scene. So this will be everything for today from the color lecture. You have, besides the well-known RGB color space, learned about the other color spaces which can be practical for various purposes, also including the imaginary color spaces like XYZ, which is useful for conversion. We have learned about perceptual uniformity and color spaces associated with that, and also about possible color spaces which are taking into account the environment, like the LAB color space, and the adaptation capabilities of our visual system and how this can be modeled. That's all from me for today. Thank you very much.